Hi, welcome back. Today we're going to be talking about iterative phase estimation, as well as also giving a little bit of a refresher to people on how measurement works. Much of the discussion on iterative phase estimation that I'm going to be giving today will be lifted from not the textbook, but a paper by Hastings, Friedman, and Savori called faster phase estimation. So if any of you want to get a better idea about how this all works, I recommend you take a look at that reference. But in any case, let's start working. So the idea basically behind phase estimation is that what we want to do is we want to be able to find a way of estimating or sampling from the eigenvalues of a matrix. So recall, for those of you who haven't looked at eigenvalues for a while, we say that a vector v is an eigenvector, where eigen just means characteristic, of a unitary operation u if uv equals e to the I theta v. Okay? Now, in this particular case, in general for an eigenvector, you would have some constant out here. This is called the eigenvalue. So it's the constant that the matrix ends up multiplying its eigenvector by in order to get back itself. And it's the definition of an eigenvector is just, it's a vector such that when the matrix acts on the vector, you get the vector back times a constant. Now the eigenvalue here for a unitary matrix has to be of the form e to the I theta v. The reason why is because we know that v inner producted with v is equal to 1. And that is equal to the inner product of v with u dagger u v, because these two cancel each other. Okay, cool. But if we assume that that's the eigenvalue, then we end up getting that, if we instead took the eigenvalue to be lambda, this would be lambda star lambda v inner producted with v equals lambda star lambda, which is the absolute value of lambda squared by definition. Okay, now this has to be equal to 1, and so this implies the absolute value of lambda equals 1. Now lambda's a scalar, and so all solutions to this equation can be expressed by writing lambda is equal to e to the, let's make it plus, I theta v. So without loss of generality, we can assume that the eigenvalues are e to the I theta v. Okay, so why do we care about this? Well, there's a couple of reasons why we deeply care about this. It's because of the fact that eigenvalues are typically very hard to estimate using classical computers. In fact, actually, the problem of figuring out the ground state eigenvalue for chemistry is actually the central one that people try to struggle when they're trying to compute reaction dynamics effectively. And so the problem of finding eigenvalues is crucial, and it's something that a quantum computer can in some circumstances provide a huge advantage for. And I'm going to show you a way of doing that. But in order to do this, based on some of the feedback that I ended up getting, I'm going to actually take a slightly different route. I'm going to first do a little bit of a review of how measurement works and provide a new formalism that kind of encapsulates a lot of the things that we've been doing implicitly so far, but shows you how to explicitly do things like partial measurement. All right, so I'll begin with that, and then I'll show how this eigenvalue estimation procedure ends up working. Also, it should be noted that this eigenvalue estimation is going to be is incredibly important for algorithms like Shor's algorithm, as well as of value for some versions of the linear systems algorithm. Okay, so let's go ahead and look at measurement yet again, the most confusing thing in quantum theory. Okay, so now again, recall the properties of measurement. So, if we have a state psi, which is of the form sum over x square root px e to the I theta x, then the probability that you measure x at the end of the circuit is just equal to p sub x. Okay, that's the definition for that. Now, what we did last time is we showed, okay, well, we can actually take a look at measuring the probabilities of different configurations inside a set. So say we end up formalizing it like this. Let S be a set of x values and let P be a projector onto the set. Where by projector, what I mean is that the projector P satisfies with P squared equals P. And in particular, for all inputs x, Px equals x if and only if x is in the set in question and is equal to 0 otherwise. All right, so let me give you an example of, all right, so if we have this, then the probability that some vector y is measured to be in this set is then psi p psi, okay? And so if we can write some set of equivalent configurations whose probability we want to measure, we can estimate it just by computing the expectation value of that quantity. So that's a very nice feature, but let me give you an example. And I think I gave this example before, but let's say we want to do Fibonacci numbers. Okay, so we want to figure out the probability of drawing a Fibonacci number when you sample. So in this case, the set S in this case would be 1, 2, 3, 5, 8, so on and so forth. Now, the matrix P in Dirac notation can be written in the following form. It can be written as 1 plus 2 plus 3 plus 5 plus so on and so forth, going all the way through. Okay, and so that is how we would end up writing the projector. And if we were to draw this out as a matrix, the matrix would look like this, for example. Okay, and so we can figure out the probability of, for any arbitrary state of computing a Fibonacci number, is just psi p psi. And this is actually really obvious what this is going to be. This is just psi inner producted with 1, absolute value squared, plus the psi inner producted with 2, absolute value squared, plus psi inner producted with 3 squared, plus 5 squared. So the way to look at it is this is equal to the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 5, which is exactly what you end up getting from the rules of probability after recognizing that all of these measurement outcomes are mutually independent. And so the probability that, that you're in a union is just the sum of the probabilities by the union bound, because the intersection is 0. So that's one way we can compute it. Now, this is useful, but it falls a little bit short. And so not quite the full formalism for measurement. That requires a slightly more complicated concept called a POVM. But I'll show you the next best thing, which is called a PVM, or projector valued measurements. So the idea about this is to actually kind of formalize what we mean by a measurement, and talk about what a partial measurement explicitly is doing for a state. So let's say that, as a particular example, what we end up getting is we have the state, let's say 1 over root 2, 0, 0, plus 1, 1. And let's say that we measure the first qubit over here, and we get the outcome 0. Then we all know that if we measure this to be 0, then the resulting state has to be 0, 0. So the second one has to be 0. Okay, so we know that these sorts of rules happen, but measurement, it can sometimes be more subtle than that, and the degree of entanglement here, or correlation, that we see is total. So it may not be quite as total in general. So let's define what a PVM is, which generalizes this notion of saying what the residual state is upon a measurement. Okay, so a PVM, M acting on M qubits satisfies now we'll let following be a set of orthonormal vectors. Okay, think computational basis states, but in general these could be anything we want. Then for all psi and p and 1 through 2 to the m, the actually, you know what, let's start from 0 to 2 to the m minus 1. Be good computer scientists for once. And then the PVM M maps psi to phi p tensor identity psi divided through by square root of psi phi p tensor I psi with probability. So this is not a deterministic map. Absolute value of psi phi p tensor identity psi. So this is just an elaboration on the rule that we discussed previously. The probability of performing a measurement over here and getting outcome phi p is just the expectation value of that projector. And we can see that this is a projector, hence earning it its a moniker, because phi p tensor identity squared is equal to itself. Okay, so therefore this is a projector, because projectors are defined to be matrices such that when you square them, you get itself back. Cool. All right, so that is the definition of a PVM. So the way that you can think about it, doing a partial measurement on a quantum computer, is that you measure an outcome and then you apply the projector corresponding to that outcome to the state. And here, these are the qubits not measured. So in the case of the Bell state that I did earlier, this would be, now if our POVM that we're taking a look at, or sorry, PVM that we're taking a look at, has phi 1 or phi 0 equals 0 and phi 1 equals 1. Now measuring the first qubit using these two things, we will, with probability 1/2, map psi to 1 over root 2, 0, 0 tensor identity acting on 0, 0 plus 1, 1. Okay, and that is equal to just, well, 1 over root 2, 0, 0. Now, divided by, of course, the length of this vector, which, when we do it, is going to give us 1 over root 2 on the denominator. So those two cancel, and we get the same result that we intuited from our earlier stuff. So this approach of PVMs gives you a way of linear algebraically following a lot of the intuition that we've been doing in the past, and gives you a way to solve these problems without really kind of the same sort of intuitive thinking that we've needed to do in the past. So that's how we do a PVM. Okay, so this notion is going to be really useful going forward. But there's one other property of measurement that I would like to talk about. It is the principle of deferred measurement. And the principle of deferred measurement, Nielsen and Chuang speaks at lengths about this. But the idea basically behind it is that if you've got a measurement over here that classically controls a unitary, this is equivalent to doing a quantumly controlled unitary immediately followed by a measurement. And so we can do this in order to be able to find equivalent circuits that shift the measurement further down. So an example of this is, let's say we're doing teleportation, where we've got Alice holding a copy of psi, and Alice and Bob beginning with just 0 states. You feed in a Hadamard, you do a C0 down here, then you do a C0 and a Hadamard at the top, measure, and measure. And I forget exactly which one is which, but I think this one's a X, I think this one's a Z. But it doesn't really matter for the purposes of this example. So using the principle of deferred measurement, the statistics that we would get by doing this circuit is equal to the same statistics that we would end up getting by doing the following. And so typically we can use this in order to push all the measurements further to the right. And in general, if we don't want to reuse any of these qubits, and we assume that we can keep on adding extra quantum bits, we can actually make all such measurements occur at the very end of the protocol. And that can be very useful for analyzing what happens for quantum algorithms in general. So that's the principle of deferred measurement. Now we're going to use these ideas put together to solve the problem of estimating eigenvalues. And this process is called iterative phase estimation. Now, typically, the way that actually people teach this material is they usually teach you about this technique called a quantum Fourier transform. But given the fact that we've talked about the swap and the Hadamard tests recently, I thought actually it's a lot more straightforward for us to skip a step and go straight to phase estimation before we talk about quantum Fourier transform, because actually it's not needed in order to estimate an eigenvalue. So let's begin by assuming we've got a unitary U. And then this unitary has a property that, of course, U acting on V is equal to e to the I theta V, V. Now, we're going to want to estimate theta V. And the way we're going to do this is we're going to actually build an interferometer. So just to give you an idea for the computer scientists who are the majority of this class, what an interferometer is it's actually a technique that began in the 19th century, and it involves sending light onto a half-slivered mirror. The light separates into two branches. In one branch, phase is allowed to accumulate by changing the path length effectively that the light travels. And then what we do is we combine these two beams of light back together. Now the light ends up picking up a different phase if it goes to the top or the bottom. And the probability that it ends up either going through or bouncing back actually ends up depending on the phase difference. And so, you'll get some probability that it ends up that a single photon from this will go down this of cosine theta squared, or cosine phi squared over 2, I think. But in any case, and this one will, of course, be sine squared phi over 2. So we're going to want to do the exact same thing. What we're going to want to do is we're going to want to break our experiment up into two different branches, one of which we are going to apply a phase, this theta v in, and the other branch we're not going to do anything in. And so the way this algorithm ends up working is just like the previous ones. We begin with an ancilla qubit. This ancilla qubit over here, what it does is it tracks the path that we're going through the algorithm. This path would correspond to 0, and that path would correspond to 1. And so we will split it into a 50-50 superposition of the two by applying the Hadamard gate. Now, down below, I'm going to assume we've got the eigenvector v. Now, we want to be able to apply the phase only on one of the two branches. And so we'll do that by applying a controlled unitary. Then I'm going to throw in this. Now, this part is technically not necessary for the protocol, but it's really useful for some algorithms involving it. Oh, and I should mention, we're going to apply this m times. So not just the ordinary unitary, we'll do it m times. And we can always do that because if we want to look at simply, controlled u squared, that's just equal to 2 controlled u's right after each other. So we can always do powers just by sequentially doing them. But I'm going to put through a RZ dagger, I believe, of this Hadamard, and you guessed it, measure. No, I did not waste your time with all of that discussion earlier. So this is the protocol. Notice that it looks exactly like the Hadamard test. So let's go through the logic and see what ends up happening. So our initial state is 0v. We apply the Hadamard transform. That ends up mapping us to 1 over root 2, 0, v, plus 1, v. which is the analog of this beam splitter at the beginning of the protocol. Now, we apply our controlled unitary. The controlled unitary maps this to 1 over root 2. Now, it doesn't do anything on the branch where there's 0 in it, but it'll apply 1 and u to the mth power on v over here. However, v is an eigenstate. And so because it's an eigenstate, otherwise called an eigenvector, the two are synonymous, we end up getting e to the I called it theta v times m over here, v, 1. Okay, now we apply the rotation, and the rotation will end up giving us 0v e to the I theta v minus omega times m 1 v. Just by this definition over here of RZ. So now, what we're going to do, oh, and there should be a plus sign still in between. Now we need to do a final Hadamard transform. And the final Hadamard transform, again, just like it did with the swap test, will map us to 0v 1 plus e to the I m theta v minus omega plus 1v 1 plus e to the negative I, plus I m, this should be a minus theta v minus omega. Okay, great. And so now, let's assume that if we measure first qubit and get 0, then we map the state. Let's call this thing psi over here. Then psi maps to 0 tensor identity psi. Okay, divided through by some normalization condition. So this corresponds, if we just do this measurement, we see, oh, hey, that is just 0v. This scalar over here, we can actually just use some trig to do that. Using Euler's identity and a little bit of trigonometry, we end up actually finding that the probability of measuring this is cosine squared m theta v minus omega over 2. Okay? And that is the essence of phase estimation. So we've done an experiment that ends up giving us the ability to extract the phase just from measuring the probability. Of course, the way that we're going to do this is actually much more subtle than this. We're going to try to do this far, far faster. But let's look at the dumb way of doing it before we start talking about the intelligent way. So the dumb way is, let's call this dumb, PE. Okay, the way dumb phase estimation would work is we choose a value for m, and we choose omega. We can pick anything. We can pick them randomly if we feel like. Then what we do is repeat experiment n times. And we take P of 0 equals the number of zeros measured divided by n. So we just take the sample frequency as our estimator for the probability in using statistical language. So that's what p of 0 is. Now this is equal to cosine squared m theta v minus omega over 2. Okay. So doing a little bit of math, we end up finding that theta v then, which is the logarithm of the eigenvalue that we want to estimate, is equal to arc cosine of the square root of this empirical probability of 0 that we measured, times 2 plus over m plus omega. Okay. And that is how we can estimate it. We do this experiment over and over and over again. Now, there's a little bit of subtlety that ends up coming in, because if we want to learn the phase value, theta v, then theta v is between 0 and 2 pi. So this isn't exactly a one-to-one mapping. We have to choose a particular branch of it in order to be able to do this. But that's not the end of the world. If we only are interested in the e to the I theta v, where again, we end up having uv is defined to be equal to e to the I theta v. If we're interested in this object, not the theta v, then that's fine. Any 2 pi wraparounds that we end up getting isn't that big of a deal. But in many other cases, which we'll get to later when we talk about quantum simulation, we actually are going to care about this particular value of theta v. But at the moment, we're kind of okay. So our task is to identify this, and the way we're going to do it is we're really just going to learn theta v. Cool. And this gives you a formula for it. But the question is, how many measurements do we need? The number of measurements that we end up needing in order to be able to achieve this comes from the standard deviation of the sample mean. The standard deviation of the sample mean, this is a very important thing to know. When you try to estimate this, the uncertainty in this calculation is, let's call it delta p of 0 is equal to the standard deviation for the data set that we end up getting divided by square root n. Because the data set consists of just 0 and 1 data, this is less than or equal to 1 over square root n. So if we want the uncertainty, it turns out if we want delta theta v to be less than or equal to epsilon, then it behooves us to take n to scale as 1 over epsilon squared. So to give you an idea, roughly speaking, if we want to have an error in our estimate that is 10 to the minus 3, then we're going to need to repeat our experiment approximately 10 to the 6 times. All right, and that's a lot for a relatively small, a relatively large uncertainty. And so all of the rest of the art in this field boils down to reducing the number of measurements and or the values of m, which are the number of times that we end up applying the unitary. So in this case, if we take a look at the number of times that we end up applying the unitary, the number of u's needed is actually really just n times m, right? Because every time we apply this circuit for this dumb version of phase estimation, we're applying the unitary in question m times. So the number of controlled unitaries is nm, which is, as mentioned, in order m over epsilon squared. Okay. And so if we're counting the number of gates that we need in order to execute this, in order to learn it, that's the scaling. However, we're going to do a little bit better than this. But before we end up doing that, I want to be able to show you what happens when we do this, not just on an eigenvector. Because recall, this analysis assumed that we feed in a particular eigenvector down here. But in general, we're not going to have that. We're going to have some quantum state psi, which is totally unknown in here. And so we'd like to be able to expand it. General inputs. Okay, so it turns out there's something amazing about unitary matrices. So unitary matrices, it turns out, and this is also true for Hermitian. In fact, actually, the proof for unitary matrices, I believe, follows from, I think, Stone's theorem, it's called, which relates unitary matrices to exponentials of Hermitian matrices. And then this property is proven for Hermitian matrices, but in any case, unitary matrices have orthonormal eigenvectors. Or more accurately, you can always choose the eigenvectors of any unitary matrix to be orthonormal. Okay, great. So what that means is that if there's they have a set of orthonormal eigenvectors, and on top of that, it has 2 to the n of them. This implies that it has a complete set of orthonormal eigenvectors. And because it has a complete set of orthonormal eigenvectors, we can always view these eigenvectors as a basis to represent the problem. So for example, if we had psi equals sum over j, a sub j, j, we can rewrite this in terms of the eigenvectors of the matrix. And so we could also write this as sum over j, call it alpha j, vj, where here, alpha j is just given by sum over k Okay, sorry. Yeah, it's just given by the inner products, essentially, between the two. But that is, we're going to use this fact to say that, okay, well, if we have an arbitrary state that's input of this form, I'm actually going to rewrite this in a slightly different way. And I alluded to this in a previous lecture. This I'm going to rewrite as just the square root of p sub j, bj, where these are all the amplitudes of this. There's technically an e to the I theta that I could put in, but I can always, without loss of generality, absorb those into the definition of the eigenvectors. So this is cool enough for our purposes. So now we've got this particular state. So the question is, well, what happens to it when we end up doing iterative phase estimation? Well, by linearity, we end up getting that this ends up mapping to, after doing a little bit of trigonometric simplification, it ends up mapping to sum over square root p sub j, 0, cosine theta minus omega j m over 2 plus 1 I think I need an I here, actually. Sine of theta j minus omega m over 2. And then all of this, of course, is multiplied through by Vj on that side. Okay, cool. So that is when we apply the circuit, save the measurement, this is the result that we end up getting to using iterative phase estimation. Okay, great. And so now let's take a look at this. I'm going to call this term over here P of 0 given theta j and m and omega. This over here I'm going to call, or actually I'll call it the square root of that. Square root of the probability of 1 given theta j, m, and omega. This is a semicolon, not a j, by the way. Okay, so that is the expression that that we end up getting. So when we rewrite this, we can assume we measure 0. Okay, if we measure 1, then something very similar will end up happening. But if we measure 0, then this ends up becoming the sum over j, pj, I'll put a 0 out here just to be pedantic, multiplied through by p of 0 given theta j, semicolon, m and omega, and divided through by the normalization factor, which I'm just going to call square root p of 0 because it gives us the probability of measuring 0, irrespective of what that value of theta j is. Okay, cool. So then that's multiplied by Vj. So if we take a look at the updates of the amplitudes, what we end up getting is that the amplitude Pj maps to square root of Pj times P of 0 given theta j, semicolon, m, and omega, divided through by P of 0. Okay, so actually, this is really kind of neat. And this actually is true for a partial measurement more broadly. But the way that the coefficients are being updated is actually identical to Bayes' theorem. Except Bayes' theorem doesn't have the square root. So Bayes' theorem ends up saying that for any event E and for any hypothesis theta, the probability of theta given E is equal to the probability of the prior probability of theta that you ascribe times the likelihood that E would occur given hypothesis theta being correct, divided through by this normalizing constant called P of E. And you'll note that this is exactly that form. So what happens when we're doing a step of Bayes' theorem, right? So if we do Bayes' theorem and we take a look at the objects in here, this object is called a prior probability distribution. Now, there's many ways that you can interpret a prior probability, depending on if you're a Bayesian or a frequentist, and I do not want to get into that knife fight. But the basic idea behind this is that this prior probability actually serves a very analogous role to our wave function amplitudes, our PJs over here. And the way measurement updates these values is just like the way that Bayes' theorem says we should update our probabilities based on that. So that is the connection. And the neat part about it is that this prior probability, when people normally apply Bayesian inference, this is a number. It's like a quantity in a vector that we're keeping track of. In this case, it's the wave function amplitude itself. So it's almost as if the wave function applies Bayesian inference on its own value. So it's kind of like as you start feeding more and more data and start doing more and more of these partial measurements. So let's just go back to this over here. So the way that you would do this over and over again is note that if you put in V over here, we argued that V comes out the other side. So we can always, and I'm going to write it in a form that's more friendly for the principle of deferred measurement, we can always end up just doing the same thing over and over and over again. And every time we do this, it's going to provide more and more evidence and update our amplitudes according to this. And so what will happen actually is that this expression only has a relatively small, only has a couple of fixed points. In fact, this recurrence relation that we end up getting over here, we can easily show will only be stationary if and only if Pj is a delta function, i.e. if and only if the wave function is an eigenvector. So, by applying iterative phase estimation, you collapse onto one of the theta sub j's. And in fact, actually, the probability of getting theta sub j in this is actually just equal to Pj. So, depending on what the initial prior probability of, or the support of that particular eigenvalue, that'll determine the probability that iterative phase estimation ends up yielding the correct value. However, in order to be able to see that this process ends up converging, the easiest way to do this is to actually just take a look at the fixed points for this map. So, fixed point, we'll note this, so the fixed points for the map can be found by figuring out what the fixed points of Pj goes to Pj divided by P of E given given theta. I'm going to suppress the values of m and omega here because they're not super duper needed for the argument. So this is what happens when we measure and we get an outcome E, where here E is either going to be 0 or 1. Okay? So regardless, the values of Pj update the exact same way they do for Bayes' theorem. Cool. So now let's argue that this is that the following is a fixed point. So let's let Pj equal to Kronecker delta function j and m, i.e. Pj is equal to 0, 1, 0, all the way down. So there's just one entry where it's non-zero, located at j equals m. Okay, so if that's the case, then what ends up happening? Well, we end up having on the left delta jm, right? And on the right, this is going to end up mapping to delta jm multiplied by some probability, p of e given theta, I'll be very clear here, j. Now the normalization condition actually could just be found by summing over this. That is going to be the sum over j, p of e given theta j, delta j m. Okay? And so this is actually just equal to delta jm. So therefore, this is a fixed point for the map. Now, let's assume that we end up having that our map has the following structure. Let's say that we end up having two components that are non-zero. So let's say that p sub j is equal to a delta jm plus b delta jk for a plus b equals 1. Okay, fantastic. Now we end up getting that a delta jm plus b delta jk maps to a delta jm p of e given theta j plus b delta jk p of e given theta j divided through by the normalization, which is, once we do the sum, we end up getting a p of e given theta m plus b p e given theta k. All right, cool. So let's take a look at when this whole thing is equal to the original. So it's going to be equal to the original when the top and bottom, well, the ratio between the first two terms on the top have to be the same. So we have to have that p of e given theta j equals p of e given theta k. Okay, that's the only way that that's going to happen. Now, when we divide through by, if we have that, and we divide through by this, then we end up getting 1 down here, so everything's all cool. So this is the criteria for it. Now, if we assume theta j and theta k both are distinct and are not rational multiples of pi, then the probability over randomly generated instances of E data that the results are going to be the same is basically 0. So we know that in the event that these values of theta j and theta k, if they're not in some sense equivalent to each other, then life is good. And the fixed points that we end up getting are in fact just going to be the eigenvectors of the unitary. So furthermore, because the map has value less than or equal to 1, it projects onto most likely theta j given the experimental data. Okay, so you can see basically because of the fact that this ends up, this update process ends up multiplying our amplitudes further by a constant which is less than 1 in the numerator up here, what will happen is that this procedure will geometrically converge down to one of these points. And the only way that we can end up having a vector that ends up being a fixed point is if actually there's only one component in the probability distribution that is non-zero. Again, it's possible for others to be non-zero, but in order to end up getting a stationary distribution for this, we have to assume that both of those hypotheses yield the same probability, i.e. theta j is equal to theta k. And now if they are not rational multiples of pi, then, well, and they're distinct numbers, that can never happen. So that shows that in general, applying PE yields an eigenstate. Further, how can we go about learning the phase? As experimental data goes to infinity. So, learning a eigenphase. So, the entire learning process in iterative phase estimation, and where the eigenphase again is jargon for the eigenvalue, the logarithm of the eigenvalue theta j. So, how do we go about doing this? Well, the way that the simplest way of doing this is actually just to infer what the value of theta j is. So, we can do that actually just using Bayesian inference. So, for example, the probability, let's say we've got a data record of sorry, let me just make sure I've unified my notation in these notes. Cool. Yeah, let's assume that we have outcomes E1 through En over here. And what we would like to be able to do is we'd like to be able to estimate the value of theta j, given all of those outcomes. Well, we can use Bayesian inference in order to be able to figure out what the posterior, it's jargon for the probability, of theta j is given this sequence of measurements, E1 through En. Because all of these measurements that are done are statistically independent, this actually is just equal to the prior probability multiplied through by all the likelihoods of all the experiments that we're doing. J equals 1 to N of P of theta J given E J. And implicitly, of course, this is going to be a function of the net value of M that's taken at each of them and omega that's taken at each of them. But I'm suppressing that for notational simplicity. Okay, so this ends up giving us our prior probability. Now we can take our initial prior over here to be uniform. Say we don't have any knowledge when we begin the protocol of what the phase is, in which case we were going to set our knowledge of the phase to be just uniform distribution, just 1 over 2 pi. Or at least this will be the density of it. But the way that we can envision doing this is, let's imagine that we break up the domain 0 to 2 pi into 2 to the little m bins. Okay, and technically I guess there's, yeah. So then what we have is we have that given m bits of precision, we can take a look at this discretized prior probability distribution, and we want to ask, what is the probability that we end up getting a result that's between 2 of these little windows up there? Okay, and so in that case, what we can do is we can just say, okay, well, I'm going to take the midpoint over here to be, I don't know, theta 1, theta 2, going all the way up to theta 2 to the m minus 1. Okay, now, the once we've done that, we can end up just taking P of theta j in this now discrete version where we only don't have a continuum, we've got individual bins, is just going to be 1 over 2 to the m minus 1. So this is just the probability of each of them being equal. So if we end up making that assumption, then Bayesian inference becomes a lot easier. Then the probability for any j, that theta j is true given all these values, is just proportional to the product from j equals 1 to n of P of theta j ej. And so the most likely theta j is equal to the argmax over j of the pi from j equals 1 to n P of theta j given ej, where again this probability is going to be of the form for ej equals 0, it will be cosine squared mj times theta j minus omega j divided by 2. Okay, so that's how you can find or infer the most likely value. You basically just end up using gradient descent or some other algorithm like that in order to be able to yield this. If instead you want to also quantify your uncertainty in the phase that ends up coming out, then explicitly tracking a probability distribution over the thetas is a really good idea. But in any case, you might ask, okay, well, how do you pick the mj and theta j? Well, it turns out that the values, that way I suggested previously, just picking a fixed value is almost as dumb as you possibly could end up getting. Because as mentioned before, if you pick mj just to be some constant, is then it's upper bounded by the constant function, then what we end up getting is that in that particular case, the number of measurements we need is equal order 1 over epsilon squared. Okay. So that means if we want to be able to achieve error epsilon in our estimate of a eigenvalue, no promises which eigenvalue you get, because that probability, it depends on these amplitudes up here, the little pj's. So that those depend on the overlap between them, not our uncertainty about what the individual eigenvalue is, which is what we're tracking down here. So, no promises about which eigenvalue you're going to get in the end, but you'll get an eigenvalue once you collect enough data, and your uncertainty in that is going to be order 1 over epsilon squared. Okay, but the question is, can we play a game like 20 questions? So what ends up happening is that as we start asking more and more questions, we start out with kind of a uniform distribution over the phase. We have no idea about which value from, theta equals 0 to 2 pi is the correct one. Now, as we start collecting more and more data, some of these hypotheses are going to start becoming less and less likely. And we'll start getting a spike near some of the values over here. And this spike will correspond to, once we've hit this spike, what ends up happening is the most of the data that we are going to end up getting will be consistent with just a couple of data points. And so our experiments aren't going to be very good for distinguishing between this hypothesis and that hypothesis. But by stretching out the value of m, because the probability ends up going like cosine squared m theta sub j over 2, by making m larger and larger, what we can do is we can actually amplify this effect. So we can cause these over here to have radically different probabilities just by making m sufficiently large. And that's the idea. We pick m in general, exponentially increasing, and this exponentially increasing sequence allows us to play 20 questions. And what I mean by 20 questions is that we can do an experiment to say, okay, well, let's draw a line here and say, for this given experiment, the probability that we are on this side over here should be p equals 2/3. Now, say we don't see it. Then we know we're on this branch. And we can repeat this process over and over and over again and use a log 1 over epsilon measurements to identify phase. Now, there's a number of different phase estimation methods that have been proposed. The first one was by Kitaayev, in his textbook. Also, the reference to the faster phase estimation paper has good pseudocode for that. Then another reference for this that came out later is robust phase estimation, and Kimmel and co-authors did that one. And faster phase estimation, which I mentioned before, is another good reference for this. And that is Hastings et al. And then I've done some stuff with co-authors on Bayesian phase estimation. But in any case, the basic idea behind all of these methods is, just to pick these sequences of experiments to be exponentially increasing in order to exponentially reduce the number of measurements. And this ends up yielding, actually, order 1 over epsilon applications of the controlled unitary operation versus the order 1 over epsilon squared applications otherwise needed. Okay, so just to give you an idea about how this such a protocol will work, let me just give you a quick recap of the phase estimation protocol, the Bayesian one proposed in the Faster PE paper. They call this information theory PE. And the basic idea is that the algorithm works as follows. We input m bits of precision. So we want to know how many bits of precision we want, which is the same thing as the number of bins in the prior distribution that I mentioned above. And we output an estimate of a theta sub j with error 1 over 2 to the m plus 1 minus 2 with high probability. And the algorithm goes like this. 1, let s is equal to ceiling log base 2 of 2 to the m minus 1 over 2, where s is the number of samples that we're going to take. So this is the number of measurements. So if we go back, this over here is what they call s. Okay, then we choose 2. We choose the mi, for I equals 1 to s do. Let m sub I taken uniformly from 1 to 2 to the m minus 1. Okay, so we pick our value, our integer value for the number of times we apply the unitary, controlled unitary for each of the s experiments, just uniformly at random. Okay, then what we do is we do the next most obvious thing. We take omega I, each of the frequencies we use for the RZ rotation, taken uniformly from the interval 0 to 2 pi. Okay, and again, remember this is a continuous value here. And perform the iterative phase estimation circuit and store result as EI. Then 3, compute theta, return theta j equals argmax of just the product over I of each of the likelihoods. Okay, and that's it. So this process, just to give you an idea, let's load up the paper, which I think is right here. So some of the data that they end up giving for this is over here. So at the beginning, what ends up happening after 10 random measurements is that the probability distribution of an eigenphase that they're estimating in this case is pretty much this spiky mess over here. But as the number of measurements ends up increasing, notice the spikes start becoming more pronounced and more periodic as the random values of m and omega start ruling out certain hypotheses. Now, also pay attention to this black star. This happens to be the true value for this. So as more data is loaded in to this approximate inference algorithm of theirs, then what ends up happening is after 30 measurements, this result starts showing decent support. But however, it's not the most likely one. They keep going, and finally, what they end up getting to, around 50, is nearly 100% support on the true value. Basically, what we need to, what we're doing is we're just combining a bunch of individual random experiments that will have non-maximal probability for most of these values. And then by repeating enough of them, we're left with just the outcome that has the highest probability, which is this. And so that is precisely how they end up suggesting that the algorithm be implemented. There's some pros and there's some cons to this. One of the big pros is that they can actually prove that this process requires order log 1 over epsilon measurements, and as mentioned, order 1 over epsilon applications of control U. So this means that if we want to learn the value of the phase within air epsilon, we can do quadratically better with this approach to phase estimation than we can do using ordinary sampling. And this quadratic advantage, which is also typically seen in applications of active learning, is a major way in which we end up speeding up quantum algorithms with respect to classical algorithms. In fact, there's many of the early algorithms in quantum machine learning were actually only getting speedups from just this technique. So this is a fantastic way for us to be able to learn eigenvalues. And we'll see later, after we end up covering Grover search, that this can also be used in order to estimate probabilities too. Just by recasting probabilities through Grover search or amplitude amplification as an eigenvalue problem. So that is iterative phase estimation in a nutshell. But I should mention that there's 3 sorts of trade-offs for iterative phase estimation. One, we want to be able to reduce the number of measurements. 2, we want to reduce number of controlled U's. Okay. And 3, we want to reduce the classical processing time. And you know what? I'll put another one in here. 4, we want to reduce the number of qubits. Because some approaches to phase estimation solve many of these problems, but they require more qubits. Others make trade-offs in different ways. For example, this approach that I showed you is optimal in terms of the number of measurements, and near optimal in the number of controlled unitaries, because it turns out that the Heisenberg limit, which can be viewed as a property of Fourier duality here, ends up saying that actually the number of CU operations that we need also is omega 1 over epsilon. So we can't do any better than this scaling in general. So quadratic advantage is optimal. However, this protocol, despite having these beautiful features, unfortunately has exponential classical processing time. The reason why is that in order to represent the prior probability distribution, we needed a vector of length 2 to the m. And so if we want to be able to get this to work for arbitrarily small values of epsilon, the computational overheads to do the processing on a classical computer are astounding. So here, this is something that there's been a lot of work on approximate Bayesian inference, for example, to be able to use, say, particle filter approximations that, instead of using a grid, model the probability density using a Monte Carlo sample of particles and move them around accordingly. There's other approaches that end up tracking everything in terms of Fourier modes and other more ad hoc approaches that try to learn the phase one bit at a time, such as Kirayev's algorithm for phase estimation. But the moral of the story is all of these make different trade-offs. Many of these that have better classical processing time will often have degraded performance in that category or this category. So depending on how exactly we want to optimize the performance of a phase estimation algorithm, we'll choose one flavor or another. And later, once we've talked about the quantum Fourier transform, I'll show an example of how to do this using a large number of quantum bits, but actually sets the classical processing time to essentially 0. So that's iterative phase estimation in a nutshell. It's one of the most important protocols for quantum computing at present, because, again, it allows us to estimate eigenvalues, which are of central importance to a number of applications. And as we go forward, I think I'm looking forward to actually being able to show you kind of more details about how these techniques can be used in order to do things like solve systems of equations. So, thank you very much.